Hello all. So in the last two lectures we discussed about the analysis procedure and design procedure of our combinational logic circuit, and next we are going to see about some of the applications of our combinational logic circuit. So one such application, we already know that arithmetic circuits are one of the examples of our combinational logic circuits, right? So here we are going to discuss about our arithmetic circuits. So why we are going to be see this is all the operations we are have to be carried out is inside the system internally in the binary combinations, right, in the 0 and 1 forms. So for implementing that, what all the procedures they have to follow, that have to be we understood, so that we have to easily construct the system likewise. So for that we have to first about the binary adders and subtractors, right? For discussing about the binary adders, first we have to discuss about the half adders and full adder concept, and then we have to go with our binary adders and BCD adders, right? So first of all, consider the if you are going to perform an arithmetic operation within a system, so all those operations are carried out in the form of zeros and ones, right? So by performing addition operation in a binary numbers on a binary number over a binary number system, so there are only 4 possible combination for us. So the first one, if 0 plus 0 it is 0, 0 plus 1 it is 1, and 1 plus 0 it is 1, and 1 plus 0 it is 10, right? So the 10 represents the sum value, the result is 0 and the carry is 1. Yes. So as we saw, we have to perform our normal addition in our decimal number system, right? So there we have this, it is a decimal number system. So we have 10 numbers, the numbers labeled from 0 to 9. Right. So after 9, if we adding 1, we get a number called 10, and from 10 if we add 1, we get a number called 11. So here it is a binary number. So the binary number system only consisting of 2 digits in its number system. So the one is 0 and another one is 1. So 1 is the biggest number having in its number system. So if we are adding 1 with 1, then it will produce a value as 10, right? And from 10 if we are adding 1, it will if we are adding 3 ones, then the result will be 11, right? So that is a process we are going to perform carried out while using our binary number system, addition for our binary number system. So here we are going to first discuss about the half order circuit. So the logic circuit that perform 2-bit information, 2-bit information as get as an input and will produce 2 bits as output, right? So that circuit we called it as a half order circuit. So here is a logic diagram of our half order circuit. So it takes 2 inputs, one is the addend bit and another one is the argument bit, and produces a sum and carry as a result, right? So this is a half order circuit. So it will consider only 2 inputs, so the 2-bit combination. So we have 4 possible combinations are having. So if we are adding that, what is the sum information and what is the carry information? So we are considering the truth table for that. So consider if we are adding 0, 0, sum is also 0, carry is also 0, right? And 0, 1, the sum is 1, carry is 0, as we know. So 1 plus 0, the sum is 1 and carry is again 0. If it is double 1, carry 0, the value of, sum is 0 and the carry is 1, right? So now we have to form the K-map for the sum variable and the carry variable, right? So we get the expression, corresponding expressions. So sum variable, it is having 2 ones, right? So the 2 ones which represents AB dash and A dash B. So which means this is a expression. If we simplify this expression, we will got A exclusive or B, right? So this is equal to A exclusive or B. And what about C? C is having only 1, 1, right? So only 1, 1 at last. So only 1, 1 which represents it is AB, right? So it is a AB. So for that we are consider the logic circuit. This is a half order circuit. So S will be XORing the 2 inputs and Y will be ANDing the 2. C will be the ANDing the 2 inputs. That will be the C, right? So this is the half order circuit, but there is a limitation with half order. So what does it means? The half adder only performs, only contains two input labels, right? So it is only have a provision to take two bits as input and add those two numbers and produce a sum and a carry. If we using half adder, so suppose consider if both the inputs I am given as in the previous lower bit addition, both the bits are 1, and so my sum is 0 and carry is 1. So for the next bit I am going to add, I am having other A and B values, but that C, the carry from the previous lower order bit cannot be added with the next higher order bit, right? So that is a drawback with our half order circuit. So this limitation of our half order is overcome in the full adder. So this is a full adder. So the full adder which will be having the 3 inputs. So this is specifically meant for our to overcome the drawback of our half orders, right? So other than the inputs A and B, it will having the C in as another one input, which will have to pass the previous lower order bits carry to the next higher bit level, right? So and it produces two outputs, some value and carry out, right? So these are all the full adder circuit. Now let us see if we are in we are having 3 bits as input, right? So we have the truth table, we have 8 possible combinations are available. So for those all possible combination, we have to produce the sum and C out value. So if all the values are 0, sum is also 0, carries are also 0. If any 1 is present, sum value is 1, carry is 0. If 2 ones are present, sum value is 0, carry is 1. If all the 3 bits are 1, then both are going to be 1, right? That is our level 11, right? Sum is 1, carry is also 1. So this is the information. So for this, if we are going to put a k-map for the variable s, output variable s and C out, we will get this. So output k-map for s which contains, so it is having 1, 2, 4, 5 and 7, right? So it is 1, 2, 5, 1, 7, yes. So if we are having connecting, we have to only add a single. So if we have to connect, we have triple combinations we get, right? So A dash B dash C in plus A dash B C in dash A B C in and then A B dash C in dash, right? So if we take from the first and third, from the first term and third term, if we take C in as common, then we will get A dash B dash plus AB, and from the second term and the fourth term, if we get C in dash as common, we get A dash B plus AB dash. So this we already know it is A exclusive or B, and this we know A dash B dash plus AB, this A exclusive or B the whole dash, right? So now it is considered the C in as our A and this is our B dash and this is our A dash and this is our B. So again it is in the form of A exclusive or B. So we can return like this as C in exclusive or A exclusive or B, right? And what about our C out? So here it is a expression for C out. So C out contain, if we merge this, so C out contain 1 and 0, 1, 2, 3, 5, 6 and 7, right? So 3, 5, 6, 7, right? So we have to form a double, 3 doubles. So the 3 doubles which will be equal to AB plus AC in plus BC in, right? Okay. So this is a logic diagram for our full order circuit. With this expression we are constructing this diagram, and this is a full order circuit. We can also implement the full order using 2 half orders. So for consider the half order circuit expression, S is equal to A exclusive or B and C is equal to AB, right? So the Boolean expression for full orders are S is equal to C in exclusive or A exclusive or B and C out is equal to AB plus AC in plus BC in, right? So if we substitute A exclusive or B as S, we can S is equal to C in exclusive or S, right? and then this is and again become it is only needs 2 input, right? So this is a simplified expression. So then simplify C out, we get, so add this term b plus b dash here, and here it is a plus a dash, we have to multiply. So then the min terms becomes like this, ab plus c in s, right? So we will see. So we will have, I am having here a, c, for convenient I am writing at the c, it is only c dash, don't confuse. So we have to add b plus b dash, right? So if we are adding b plus b dash, it is the value, nothing changes, right? So b plus b dash is equal to, always equal to 1, that we know, right? That is our idempotent, right? So that we already know. So if we are multiplying this, what we get? We get 2 terms, right? ABC plus AB dash C. So A, B, C plus A, B dash C we get. And again, if we here in this term, if we are adding A plus A dash, we get A, B, C plus A dash B C, right? So that A, B, C we will get cancel it out. So we have to consider only that A B dash C plus A dash B C. If we take C as common, we get A dash B C plus A B dash C, A B dash, right? That is, we will again consider as A exclusive or B. At A exclusive or B, we nothing but that A exclusive or is nothing but it is yes. So that we have to substitute here. So C out is equal to AB plus C in S. Yes. So with this information, we have to convert the full adder circuit using 2 half adder implementation. So this is the first half adder and this is the second half adder. So listen. So S is equal to X exclusive or Y. So that we implement. Here we produce the first S, and here it is a C out, right? This is C out, and if this, and again this is going to be given as, this is the second S2, and this is C out 2, and this will be added C in, as we know, right? C in S plus AB, that is our C out, right? So that we have to consider, and we have to get this. Yes. So this is the full adder implementation using 2 half adders. So that's all about full adders and half adders. In the next lecture, we will discuss about the binary adders and subtractors. Right? Thank you.